In this question, we've been told that a car passes a point traveling at 10 meters per second. Its motion over the next 45 seconds is modeled as follows. So then we get three distinct pieces of information. The car's speed increases uniformly from 10 meters per second to 30 meters per second. Now, just scanning down, I know that I'm about to start sketching a speed time graph to represent the information. So as I read these sentences, I'm going to try and produce the graph that accompanies it. So just starting with my axes and labeling up the velocity or the speed axis. So the car speed increases uniformly from 10 meters per second to 30 meters per second over the first 10 seconds. So I can plot the 2 points at 0 seconds, the very beginning, 10 meters per second. After 10 seconds, 30 meters per second, and I join these with a straight line. Its speed then increases uniformly to 40 meters per second over the next 15 seconds. So I need an interval of 15, and I want the velocity to go up to 40. So I've got the first two sections. The car then maintains this speed for a further 20 seconds, at which time it reaches the point. So another 20 seconds, constant velocity, maintaining a speed is going to be a horizontal line. Okay, so this is my velocity time graph, or my speed time graph, as we've been asked to make this time round. We're asked to then calculate the distance from A to B. And I think you can notice that rather than just putting on the timestamps of 10, 25, 45, I've indicated the actual differences. So 10, 15, and 20. These are much more useful when we then start to think about geometry and how to find the area of some of these shapes. So calculate the distance from A to B. We know that the distance in a velocity time graph is going to be the area. Now the area is a combination of three distinct shapes. I have a trapezium, a second trapezium, and a rectangle. And as you can see, I've labeled the dimensions on each of these shapes straight from the velocity time graph. Now, I should be able to use a simple formula for each of these shapes to find out the total area. A trapezium, half the parallel sides added together times the distance between them. Half the parallel sides added together times the distance between them. And for the rectangle, it's going to be base times height. Okay, each of these I can simply do in a calculator or in your head. We get 200, 525, and 800. 1,525 meters. That's the distance that this velocity time graph is indicating. That's the distance that the car traveled while it was being observed. That's the distance from point A, the beginning of the journey, to point B. We're then told that when the car reaches the point B, it's brought uniformly to rest in t seconds. The total distance from A is now 1,700 meters. Can we calculate a value of t? Well, I'm just going to add to the diagram here. It takes t seconds for the car to get to rest, and since it's uniform, I know it's a straight diagonal line all the way down to a velocity of 0. Okay, if the total distance traveled is 1,700, and I know up to point B was 1,525, this section here should be 175 meters. So we can once again rely on distance equals area. Distance we know, 175. The area, we know some of the dimensions, and we're looking for the unknown time interval of t. 175 equals the area of this triangle. Half times 40 times t. And with some rearranging, we get that the time is 8.75. 8.75 seconds, that's how long the car was decelerating for.